Okay, welcome everyone for today's quantum space-time seminar. Today, we are very happy to have Ofer Aharony from Weizmann, and he's going to tell us about type 2 string theory on AdS3 times S3 times T4 and its CFT dual. Ofer, please, over to you.
Okay, thank you very much for the invitation, and please let me know if there's any problem with the sound. So this talk will be based on a paper that we put out a few months ago in collaboration with AdS3. So type 2 on AdS3 cross S3 cross T4 is one of the original examples of the AdS CFT correspondence from Maldasena's paper 27 years ago. So the question is, why should we go back to it? And the answer is that in many ways, this is the best understood example of the AdS CFT correspondence. It shares with n equals 4 super Young Mills the property that it has one limit of its parameters where the field theory side is free. In this case, it's a free orbifold. While there's another limit of the parameters where the dual gravity background is weakly coupled and weakly curved so that it's well approximated by supergravity. But it also has the extra advantage that at least for some values of the parameters, also the string world sheet theory and the string perturbation theory can be understood very well so that we can understand it in much more detail than in other examples of duality. And the reasons that we went back to studying this example is that because we can study string perturbation theory in much more detail, when we tried to study it in more detail, we encountered a few confusions. And in this talk, I'll try to explain what these confusions are and how we were eventually able to resolve them. So the first 2/3, more or less, I think, of the talk will be devoted to reviewing this background because many things are known and well understood about it for many years. So I'll begin by reviewing this background from 3 different points of view, from the point of view of supergravity, from the point of view of the dual conformal field theory, and from the point of view of the string world sheet. And I'll then review also how string dualities act on various backgrounds of this type. So this will be most of the talk, I guess, and that will set up the stage for discussing 3 confusing questions about the behavior of string perturbation theory in this background. I mean, so I won't go over them now, but hopefully they'll become clearer as time goes on. So I apologize in advance that, I mean, there are many people that worked on this topic through the years, and because this is a Blackboard talk, I will not be able to give any references, so I apologize in advance. And please do stop me with questions at any time during the talk. I mean, this is a Blackboard talk, so it's completely flexible. So let me start by reviewing this background of type 2 string theory on AdS3 cross S3 cross T4 from the gravity point of view. So the starting point is we'll start from type 2b string theory on T4. We could equally well start on type 2a string theory because they're related by duality, so I'll just choose 2b to be specific. And we'll take Q5 D5 branes, wrapping the T4 and filling 2 of the other dimensions, and Q1 D1 branes that are parallel to them and they're non-compact dimensions and that sit on a point on the T4. So this each type of brane breaks half of the supersymmetry. So these 2 types of branes together break the supersymmetry to n equals 4 supersymmetry from the point of view of the 1 plus 1 dimensions that these 2 types of branes share. And then when we take the near horizon limit of this brane configuration, we get type 2b on AdS3 cross S3 cross T4, as again discussed by Maldasena's already 27 years ago. And these are branes that we started from become fluxes on this AdS space. So we have Q5 units of the Ramon 3 form flux on the S3, and we have Q1 units of the dual 7 form field strength on the S3 cross T4. So these are the basic parameters of this background. Now the fact that we have here 2 different types of fluxes means that when we take the near horizon limit, some of the asymptotic parameters of the type 2b string theory become fixed by some type of attractor mechanism, so that in the near horizon limit we actually have fewer moduli. So what we get if we take the near horizon limit, just using supergravity, we find that the 10-dimensional string coupling in this frame is arbitrary, and the radius of the AdS3, which is the same also as the radius of the S3, are given by I'll denote the string coupling in this frame by d tilde, and all the other parameters also by tildes. There'll be another frame soon, which I'll denote without tildes. So the radius of AdS in this frame is, in string units, is given by the 10-dimensional string coupling times Q5. But the volume of the 4 torus in this frame is fixed in the near horizon limit to be Q1 over Q5, again in units of the string coupling. And in this frame, you'll note that T-duality exchanges, if we do a T-duality on all 4 circles, then that exchanges the d1 branes and the d5 branes, and it also makes V tilde to 1 over V tilde consistent with this relation. And it's natural to discuss also the 6-dimensional string coupling. So as usual, we define a 6-dimensional string coupling by the volume divided by the 10-dimensional string coupling. And then if we write the radius in terms of the 6-dimensional string coupling, then it has a more symmetric expression as g6 tilde square root Q1, Q5 in units of the string frame, or just as a square root Q1, Q5 in units of the 6-dimensional Planck scale. So this relation is very similar to what we have also in AdS 5 cross S5. There we have that the radius of AdS is square root n times the Planck scale. So here we see that this combination of Q1 times Q5 plays the role of n, and obviously for supergravity to be valid, this has to be large. So we see that supergravity is valid in this background if Q1, Q5 is large, and also if we want the AdS radius to be large, then we need also that Q1 tilde Q5 has to be large. So those are the basic properties of this frame in which we can discuss AdS3 cross S3 cross T4. We can go to another frame by doing an S-duality transformation. So S-duality replaces this background by the near horizon limit of Q5 image towards 5 branes wrapped on the T4 and Q1 fundamental strings. And again, the near horizon limit is still the same AdS3 cross S3, just related by an S-duality transformation. So the string coupling in this S-dual frame is, as usual, just 1 over the string coupling in this other frame. I'll call this thermal number 1 frame, and this an SNS frame for obvious reasons. And in this frame, the radius of the AdS is just Q5 in units of the string length. Now, it turns out that the duality between these two frames, even though it's not obvious, it exchanges the role of the volume of the 4 torus in one frame with the string coupling in the other frame, so that in this SNS frame, it turns out that the 10-dimensional string coupling is arbitrary, but the 6-dimensional string coupling is fixed to be Q5 over Q1, so that in order to get recoupling in this frame, we need Q1 to be much larger than Q5, while the volume of the 4 torus in this frame is arbitrary. It can be anything we want, and of course, that's related to the 10-dimensional string coupling in the usual way. This frame, if we do a T-duality on the 4 torus, it actually goes to itself, so we can always choose the volume in this frame to be bigger than 1 if we apply some T-duality transformation. And in this frame, we see that supergravity is valid whenever Q5 is much bigger than 1, while string perturbation theory is valid if we also have that Q1 is, or if we have that Q1 is much bigger than Q5. So these are the basic properties of this AdS3 cross S3 background. It also has various additional parameters that I'll discuss in a few minutes. But first, are there any questions about these basic parameters? Okay, so if there are no questions, then let me move on to discussing what's the two-dimensional conformal field theory that's dual to this background. And as usual, to discuss it, one way to derive the conformal field theory is to start from this brane configuration, whose near horizon limit we took, and to discuss what's the low energy theory that lives on these d5 branes and d1 branes in type to be string theory. On the d5 branes, we have a 5 plus 1 dimensional UQ5 gauge theory, and that lives on this T4. And from the point of view of that gauge theory, the d1 branes look like instantons, and so if they're just d1 branes, then they're point like instantons, but if we turn on the strings between the d1 branes and the d5 branes, then these instantons can grow up to finite size instantons in a way that still preserves all the supersymmetry. So we have so this theory of the d1 branes and the d5 branes at low energies has a moduli space, which is precisely the moduli space of Q1 instantons in UQ5. And what that implies is that this two-dimensional CFT is just a supersymmetric sigma model with n equals 4 for supersymmetry.
Ofer, can you hear it?
Yes, now I can hear you. Any questions?
Hi, Ofer, sorry, can you hear?
Yes.
Great. Just go 1 minute back to the string theory part, the 2D string theory part.
Yes.
So should I think of the limit that's being taken as G times square root of Q1, Q5 held fixed with Q1, Q5 going to infinity and G going to 0, as that being sort of like the top limit of n equals 4? And then later we take...
I think that it has a meaning also in the field theory. I mean, and here in the field theory, I'm not sure if there's any analog, but in the sense that in the string background, that's what corresponds to having a fixed AdS radius and the Planck scale going to infinity, then yes. I mean, so from the gravity point of view, yes. From the field theory point of view, I'm not sure if we understand.
So that's the limit in which string theory will become classical,
Yes.
but would be string theory. Okay, thank you.
Yes, exactly. Any other questions? Okay, so when we consider the low energy field theory on these D1 branes and D5 branes, we obtain this sigma model on the moduli space of Q1 instantons of the UQ5 gauge group on T4. And this sigma model, it turns out that, well, its metric cannot receive any quantum corrections with this amount of supersymmetry, and it turns out that the sigma model is indeed a superconformal field theory. So the claim is that this is the conformal field theory, which is dual to this AdS3 cross S3 cross T4 background of type 2B string theory. Now what's the dimension of this moduli space? If we have Q1 instantons in SUQ5, then there's a famous result that the dimensions of that moduli space is 4 times Q1 times Q5. So that's the dimension of the moduli space of Q1 instantons in SUQ5 on a torus. But in this case, we don't have just SUQ5, we have also a U1 factor in the gauge loop, and that gives us 4 extra massless scalars from the Wilson lines of the U1 fields on this T4. So the full dimension of the moduli space, in this case, of the moduli space of instantons, in the sense of just flat connections of this UQ5 gauge theory, is 4Q1, Q5 plus 4, which means that this conformal field theory has a central charge which is equal to 6Q1, Q5 plus 6. And one can check that, of course, this central charge in the large Q1, Q5 limit agrees with what we found on the gravity side. Now, in general, this sigma model on the moduli space of instantons is very complicated. So this is a complicated CFT. The space has various singularities that we'll discuss later. So it's generally very complicated. But in the special case, there's one special case where it simplifies, which is the case of Q5 equals to 1. So for Q5 equals to 1, we have just a U1 gauge group, and then for U1 gauge group, we don't have any finite size instanton solutions. So in this case, all the instantons have to be of 0 size. So we have Q1 instantons of 0 size, so their moduli space is just T4 to the power of Q1 mod SQ1, since they're identical 0 size instantons. And this is just labeling their positions up to permutations on the T4. And in addition, we have the Wilson lines of the U1 gauge field on the torus, so in this case, they live on a dual torus, so in order to be mapped, I think. So in this special case, this sigma model of Q5 equals 1, this sigma model becomes very simple. It is just the sigma model of a free orbifold times a T4. Now, just these considerations of the metric don't tell us exactly which orbifold we're discussing. For instance, this orbifold has some Z2 fixed points where there are exactly marginal deformations, including a theta angle. So just from these arguments a priori, we don't know whether we sit at the singular point of this orbifold or at the what's called the free orbifold point. But I'll review later the arguments for why, in fact, this theory sits at the free orbifold point of this orbifold. So that's this special case. And again, we'll be interested in this talk in studying this theory both for the special case and for general values of Q1 and Q5. Now, what are the symmetries of this background? So of course we have this n equals 4 for superconformal symmetry, so that contains an SU2 cross SU2 symmetry for the left movers and the right movers. And these symmetries on the gravity side are just related to rotations of the S3. So obviously we have SO4 rotations that correspond to this SU2 cross SU2 group. But we also have additional currents. So if we look at, if we consider the center of mass of these Q1 instantons on the T4, that gives us 4 compact scalars that live on the T4. And these 4 compact scalars, as usual, give us a U1 cross U1 current algebra, which in this case, because we have Q1 instantons, it's at level like Q1. So we have a U1 cross U1 Q1 to the 4th current algebra coming from the center of mass positions of the instantons. And similarly, from these Wilson lines are also periodic scalars, and they give rise to a U1 Q5 cross U1 Q5 current algebra, again raised to the 4th power, and 1 for each of the 4 circles of the torus. So we have these 16 additional U1 current algebras, in addition to the, so they're not part of the superconformal symmetry, they're extra current algebras. And what do they map to in the bulk, in the dual gravity description? So they need to map to 16 U1 gauge fields that we should have in this AdS3 space. And if we look in particular in the SNS case, then we have 8 gauge fields coming from the G mu I and B mu I components of the metric and the B field in type 2B string theory. So this gives us 8 U1 gauge fields, and they turn out to be dual to these U1 cross U1 fields at level Q1. And in addition, we have 8 additional gauge fields coming from the Ramon sector, from the Ramon 2 form and 4 form. Each I take A here go from 1 to 4. Each of those gives us 4 additional fields, and they turn out to be dual to this U1 cross U1 current algebra. Now, the way that we get a current algebra is that if we look at the low energy theory for these U1 gauge fields, then they have specific Chern-Simons couplings that just come from the supergravity action for these fields on AdS3, and the Chern-Simons level of these U1 gauge fields precisely maps to the level of the current algebra in the CFT dual. And so one can show just from supergravity that these specific U1 gauge fields have Chern-Simons couplings at level Q1, and they map to these current algebras, while these Ramon fields have current algebras, have Chern-Simons level Q1, Q5 coming from supergravity, and they map to these specific U1 current algebras. So that's the full list of symmetries of this background.
Sorry, which one?
First basic review of the CFT. So yeah, any questions about the CFT?
Which one is this U1 Q1 with subscript Q1? Which type of transformation does it correspond to? Which symmetry is that? These two?
So, 8 of those U1s. So we have 4 compact scalars coming from, in the CFT, we have 4 compact scalars coming from the center of mass positions of all the instantons. So the symmetries are either the momentum or the winding corresponding to these compact scalars that come from the center of mass of the instantons. And they give those U1s. And similarly, we have 4 compact scalars from the Wilson loops of the U1. And again, they have a momentum and winding associated with them. And they give rise to these additional U1 factors.
Okay.
So the symmetries, in some cases, they're large gauge transformations. In other cases, they're sort of the duals of the compact scalars that are associated with these large gauge transformations. But I think it's easy to understand them in either case. Of course, in this special case, these U1 symmetries are completely clear. I mean, here, these U1s are just the center of mass T4s of the symmetric orbifold. So obviously, they're a level Q1 because the currents are the sum over the currents of these Q1 factors of T4. So they're a level Q4. And here, we just have these U1 Wilson lines, which in this case just give us a current algebra of level 1. So these are just standard compact scalars. But the claim is that the generalization of this is true also for other values of Q1 and Q5. And again, it's consistent with the mapping to gravity.
Oh, so this conformal field theory is the statement that the metric that this is conformal field theory with the instanton, with the somehow a natural instanton metric, or that there exists a metric which makes it conformal?
Yeah, I think it is just the classical metric on the moduli space of instantons that just induced from the gauge theory. I mean, so I think the claim is that just the classical metric on the moduli space of instantons is already conformally invariant. I think this was proven many years ago.
So
But this is just a case where we have 4-4 supersymmetry, yeah.
So the beta functions all exactly vanish.
Yes, I think so.
With this metric.
Yes, I believe that's the claim. I'm not completely sure, but yeah, I think that's true.
Oh, this is good.
Is this true for any space? Any
For any moduli space of instants? No, I don't think so. I mean, I think it is also true for K3, perhaps. But so I mean, it may be true for any space that has 4-4 supersymmetry, but definitely it's not true with less supersymmetries.
Okay.
So it depends. Okay. It does depend on the context.
So one more question that you may be coming to, but this conformal field theory is part of a family of conformal field theories. So there are exactly marginal deformations.
Right.
And,
yeah. So I'll discuss that in a moment. Yeah. I'll discuss the exactly marginal differentiations in a few minutes. So yeah. So for now, I only discussed a few parameters of these theories, but I'll discuss the full space of parameters in a few minutes. So I hope this will become clearer then. So any more questions about the CFT? Okay, so the final aspect is the string worldsheet. So again, we could try to discuss this either in the case of this Ramon-de background or in an SNS background, but of course, as usual, in the Ramon-de background, it's rather difficult to understand the string worldsheet theory, and it's still not well understood. But the nice thing is that in this case, we can have also a description that has purely an SNS fluxes. And in the case with purely an SNS fluxes, the worldsheet theory is understood. And in fact, it can be understood as just an usual RNS formalism of a superstring theory. So in this formalism, the worldsheet theory turns out to be just a product of WZW models, or more precisely of supersymmetric WZW models, with the group SL2 at level Q5 times the group SU2 at level Q5 times T4. So this combination of supersymmetric sigma models has C hat equals 10, so that it's a critical superstring theory. And it turns out that this supersymmetric WZW model at level Q5 is the same as a bosonic SU2 WZW model at level Q5 minus 2 plus 3 free fermions. That can be shown just by change of variables. So this description makes sense for Q5 bigger or equal to 2. But for those cases, it is just a standard worldsheet theory, and we can just use the usual rules of RNS superstring theory to perform perturbative string computations in this background. There are, however, some special features of this background, so I'll describe one of them now and one of them later in the talk. One special feature of this background compared to other examples of string perturbation theory is that the space-time theory has a continuous spectrum. So from the point of view of the worldsheet theory, this can be seen from the properties of representations of SL2. I mean, so if you just consider the representations of SL2, it has continuous representations, and one can show that also the spectrum of physical states in this background turns out to be continuum. From the point of view of the theory on AdS3, then this continuum comes from the so-called long strings. So if you have a fundamental string coming very close to the boundary, then naively that should cost a lot of energy because of the tension of the string. But for a specific orientation of the string, then it turns out that tension is completely cancelled by the contribution from the B field that couples to the world volume of the string, so that these fundamental strings can go to the boundary at a finite cost in energy. And that means that the radial momentum is continuous, and we find that this the space-time theory, and in particular the space-time CFT in this case, has a continuous spectrum above some mass gap, which is of order Q5. So that's Q5 is the energy of these long strings when we go all the way to the boundary, and starting at that point, we have this continuous spectrum. So that's something that we just find by quantizing the strings in this background. And we can now ask how that's consistent with the CFT. I mean, the CFT here naively is just a standard sigma model on some compact moduli space. So how could it have a continuous spectrum? And the point is that, again, for this case of Q5 bigger or equal to 2, when we have non-abelian instantons, then these non-abelian instantons can have a finite size, but they can also go to 0 size. And it turns out that when a non-abelian instanton goes to 0 size, then the instanton moduli space, the metric on the instanton moduli space is singular. So we have these 0 size instanton singularities. And it turns out that these singularities harbor a continuous spectrum. in some simple cases, for instance, if we have an instanton in SU2 that goes to 0 size, then locally that singularity looks like an R4 mod Z2. We have the 2 and 4 parameters to get to this 0 size instanton singularity. But it turns out that in this case we have this R4 mod Z2 singularity with a vanishing theta angle on the singularity, and that's well known again from the 90s to be a singular conformal field theory that has a continuous spectrum, even though classically the metric is just a metric on R4 mod Z2. Then there's a dual description of it where it looks like there's this semi-infinite throat coming out of the singularity, and there is a continuous spectrum of modes moving in this throat. Now, one thing to be careful about is that we have these R4 mod Z2 singularities showing up here in 2 different places in the CFT. One place is here in this small instanton singularity, and in this case we have this singular orbifold with a 0 theta angle, but we also have R4 mod Z2 singularities here in this orbifold that we have for Q5 equals 1, and these Z2, even though in both cases locally it looks like an R4 mod Z2 singularities, these singularities are completely different. They show up in different corners of the moduli space and so on, and there's no relation between them. And in this other case, we'll argue that in fact we have these the same R4 mod Z2 singularity, but with a theta angle equal to pi. But anyway, in this case, that occurs again only for Q5 bigger or equal to 2. We see also in the CFT that we do have these 0 size instanton singularities which harbor a continuous spectrum, and one can indeed exactly match the properties of the continuous spectrum that we find from string theory here with the ones that we find in the CFT. So we have a consistent description. So that's one string theory description that we have. Now it turns out that there is also another useful string theory description for this NSNS background case, in what's called the hybrid formalism. So I won't review this formalism here. It's some combination of the NSR and pure spinor formalisms that was originally devised by Berkovitz, Waffa, and Witten to discuss their own background, but it turns out that this hybrid formalism can also be used to discuss this background where we have purely NSNS fluxes. And in this formalism, the world suit theory turns out to be a supersymmetric sigma model on the supergroup PSU 11/2 at level Q5, again times the T4. So the world suit theory, this formalism is somewhat different, but one can show that for any value of Q5 bigger or equal to 2, this world suit theory is actually equivalent, or can be related by some change of variables to what we have in the RMS formalism. But the nice thing is that this hybrid formalism makes sense for all values of Q5, including also Q5 equals to 1. And it turns out that even though for Q5 bigger or equal to 2, this string theory has a continuous spectrum, and it has all these properties that we could see also in the RNS formalism. In the case of Q5 equal to 1, it turns out that this theory does not have a continuous spectrum. And in fact, it was shown by Gabriel, Pakumar, Eberhard, and collaborators that this theory with Q5 equals 1 is exactly dual to this free orbifold that we expect to get from the CFT side for Q5 equals 1. Namely, the string perturbation theory precisely reproduces the 1 over n, or the 1 over Q1 expansion of this free orbifold CFT. So there is in this case a detailed check of the duality, and I'll come back to that in a few minutes to discuss some extra properties of this case. But this is just a result that followed by analyzing this worldsheet theory. So are there any questions about the worldsheet description of these backgrounds? Okay, so if there are no more questions, then the last topic that I want to review is dualities, and that will also bring us back to the discussion that I skipped of what is the full space of parameters of this theory. So up to now I discussed these different backgrounds that have different fluxes, Q1 and Q5, as just completely separate theories, but in fact it turns out that they are in many cases related by string dualities, so that they actually all sit on the same parameter space. So if you just start from type 2B string theory on T4, then that has an SO55, group of dualities, which includes in it the SO44Z T-duality group, and also the SL2Z S-duality group. So these are all subgroups of this SO55Z duality group. And the moduli of type 2B string theory on T4 are in a cusset space of this SO5 mod SO5 cross SO5 modulus SO55Z. So we have, altogether, we have 25 moduli. If we just look at type 2B string theory on T4, and these moduli, 16 of them are the metric and the B field on the torus. One of them is the Dalton, and 8 additional moduli come from the Ramon-Ramon fields. We have the Ramon-Ramon scalar, which will also denote by chi. We have 6 scalars coming from the 2 form, and 1 scalar coming from the Ramon-Ramon 4 form. And together these give us the 25 scalars, which are the moduli of type 2B string theory on T4. Now, when we put in these Q1 fundamental strings, or Q1 D1 branes and Q5 D5 branes, then that breaks this duality group to just the subgroup that leaves this vector invariant. I mean, so this Q1, Q5 are part of a vector of SO55, and there's a subgroup of SO4,5Z that leaves this vector invariant. And it turns out that when we take the near horizon limit, then only this subgroup leaves this the background invariant. So when we look at this AdS3 cross S3 cross T4 background, its moduli are a smaller set, and in fact they live in the space of SO54 cross SO5 mod SO5 cross SO4, and mod is subgroup gamma, so there's some subgroup gamma of SO5,4Z that leaves this vector invariant, and this is the moduli space. So we have just 20, in this case we have just 20 massless scalars in this background. So 5 of the scalars that we originally had in type 2B string theory become massive when we go to the near horizon limit. So if we look in the case of an SNS background, so in an SNS background, all the 16 scalars coming from Gij and Dij all remain massless, and there's still the moduli of this T4. The delta has become massive. As I said, the value of the 6-dimensional string coupling is fixed to Q5 over Q1, so that has become fixed. And 4 of the Ramon-Ramon moduli, or 4 combinations of these moduli, remain massless, while the other 4 become fixed in the near horizon limit. So altogether, we have 20 parameters that remain as massless fields on this AdS3, and that therefore parameterize the conformal moduli space of this CFT. So that's the moduli space. Any questions about this? Okay, so we have this subgroup gamma that of SO54Z that leaves this vector Q1 and Q5 invariant. But any other transformation in SO55 that does not leave this vector invariant maps it to a different vector of charges. In particular, we already discussed the S-duality transformation that takes the Ramon-Ramon charges to an SNS charges. But other SO55Z transformations can be used to take any vector Q1 and Q5 if these two numbers are relatively prime, namely they don't have any common factors. So any Q1, Q5 can be related by one of these U-duality transformations to the background where we have just Q1, Q5, Q1 branes and a single D5 variant. So all of these different theories with different values of Q1 and Q5 that are relatively prime, but that have the same product, are all related by these U-duality transformations. Now, at first sight, that seems very strange because I discussed before these different theories for different values of Q1 and Q5, and their properties seem very different from each other. In particular, the properties for Q5 equals 1 seem completely different from each other. So how is that possible? So, in fact, previously I did not discuss these backgrounds for the most general values of the parameters, but I discussed them only for the case where the Ramon-Ramon scalars were taken to 0. So that's the case where we really have these string Ricci descriptions and where we have the duality to the instant on moduli space and all these other things that we discussed before. However, these string dualities in SO55Z, they do not leave the Ramon-Ramon scalars invariant, but they map the configurations with 0 Ramon-Ramon scalars with one value of the fluxes to configurations with non-zero Ramon-Ramon scalars for the other value of the fluxes, and that's why they're consistent with just the subspaces of vanishing Ramon-Ramon scalars having these very different properties that I discussed before. So for example, if I consider the background with some n,1, say in the Ramon-Ramon frame, then it has this full 20 parameter moduli space, but let me just discuss 2 of the parameters, say the delta in this case, and the Riemann scalar chi. So previously I discussed the subspace of the moduli space where the Riemann scalar vanished. So this is this moduli space, which I previously called the N1 moduli space, where you have the CFT is just this free orbifold. But again, by duality, the same theory is related to other theories with other values of the fluxes. For instance, if n is even, then I can transform these parameters to the parameters of n over 2, comma 2. And it turns out that there's an arc here in this moduli space. So this arc maps to the moduli space of this n over 2, comma 2 theory, where its Riemann scalars vanish. And you see that from the point of view of the original theory, to get to this locus of the moduli space, that is the one I described before, and which I before called Q5 equals to 2. To get to here, I have to both turn on the Riemann coupling, and also I have to take the string coupling to be large. So obviously this is not described by the original string perturbation theory of this background, but it is still all part of the same moduli space. I mean, all of these parameters are continuous, and by turning on the Riemann scalar and the string coupling, I can go to this other locus, which describes this n over 2, comma 2 CFT. Similarly, if n is divisible by 3, I have here some other locus, which maps to the n over 3, comma 3 CFT, and so on. So in general, for any partition of n into two factors that are relatively prime, there is some locus that all sits on the same moduli space, where we have that theory with vanishing Riemann scalars, such that it is dual to the CFTs that I described before, both from the point of view of the spacetime CFT and from the point of view of the worldsheet. And in general, they all sit together on the same 20 parameter moduli space, which again is parameterized by these 20 scalars that I discussed before. So are there any questions about this?
And what is the description of changing these moduli in the conformal field theory and the instanton moduli space?
Yeah, so I should explain what these moduli are here. Well, in general, in the instanton moduli space, they're pretty complicated. I mean, they can be thought of as but it is relatively easy to understand them in this special case of the free orbifold. So in this case, we have the obvious 16 moduli of the T4, but we have these Z2 singularities, and at each of these Z2 singularities, we have 4 blow-up modes, so they correspond to the extra 4 parameters, and in particular, here, when I'm moving away from this locus by turning on the Riemann scalar, corresponds to turning on some of these blow-up moduli of these Z2 singularities. And similarly, also, the other moduli spaces, as I said, they also have these small instanton singularities, so close to those singularities. Similarly, we have these blow-up modes, and more generally, I mean, there are some other deformations of the sigma model that take us away from the classical moduli space of instantons, I mean, and enlarge it by these additional moduli.
So is this like making the instantons non-commutative? Is it like moving on making a non-commutative deformation of the space of instantons from the point of view of the instanton moduli space?
Yeah, I think in some cases they may be viewed like that. I mean, because some background, they can always be viewed, as I said, as turning on these background Riemann fluxes, and in some cases, background Riemann fluxes can be viewed as making the space non-commutative, but I'm not completely sure of that. I mean, anyway, I don't want to discuss any more details of the precise moduli space of instantons in this case, but again, as a CFT, clearly it does have all these deformations, and again, all these different CFTs on all these different moduli spaces of instantons. The claim is that they all sit on the same 20-dimensional moduli space of parameters, where again, it has these subspaces where it's exactly an instanton moduli space, and otherwise, we move away from it by these other exactly marginal deformations.
Just one more. What is the precise relationship between the instanton sigma model and instanton moduli space and this symmetric product that you were talking about?
So the symmetric product is the instanton moduli space for the special case of Q5 equals to 1, where you have a U1 gauge group. So in that special case, it is the instanton moduli space, but for any other case, if Q1 and Q5 are relatively prime, then the claim is that they can always be related to this case of Q5 equals to 1 by these dualities. So the claim is that all these other instanton moduli spaces, even though they look very complicated, then if I turn on all 20 exactly marginal deformations of this sigma model on the instanton moduli space, that can always take me from any one of these sigma models to this free orbifold space. So the claim is that all these moduli spaces of instantons, complicated as they may look like, all sit on the same conformal moduli space as this symmetric orbifold. Again, as long as Q1 and Q5 are relatively prime, but not otherwise.
Okay, thanks a lot.
But of course, that's a highly non-trivial property. I mean, from the point of view of course, geometry of its moduli spaces and so on. I mean, I doubt if mathematicians would know that property, but again, it is a property of the conformal field theory that we get from the signal model on these moduli spaces.
Sorry, Ofer, maybe you said this, but so this is if I just consider the modular space as a geometry, then what is the statement that relates the two spaces? That these moduli become some geometric moduli, or these are string theory?
Well, some of them are geometric. I mean, so say in this orbifold points, I mean, some of the moduli are geometric. Other ones are, I mean, there are the blow-up modes of this D2 singularity, which are sort of geometric. I mean, but they're hidden at the singular point. And there's also the B field. And of course, there are also the B fields that do play an important role, and they're not completely geometrical. I mean, so I think some of them are geometrical, while otherwise are, I mean, generalizations of geometry. So I'm not sure if I would say that
needs all of them for these dualities, right?
But yeah, but all of them are parameters of the sigma model, and they can all be seen by starting from the U1, U5 theory and turning on the appropriate fluxes. But not all of them, I suppose, would be called geometrical by mathematicians. There is one issue that you should object to at this stage. So I said that all these different CFTs sit on the same conformal moduli space, but at first sight that looks impossible because they have different symmetries. As I said, these different CFTs have U1 symmetries at different levels. So how is it possible that they could be on the same conformal moduli space? So the answer is that actually I did not so far completely describe the moduli space, and these CFTs actually have additional moduli, because we have these extra 16 U1 symmetries, say Ji and Ji tilde, and whenever I have a CFT with U1 symmetries, then there are also additional exactly marginal deformations, which are JJ bar deformations. So I can take here 64, I mean 8 left moving currents times any one of the 8 right moving currents and get an additional exactly marginal deformations. So the full conformal moduli space has 20 sort of, in some sense, single trace deformations that correspond to standard supergravity massless fields on AdS3, but there are also 64 additional exactly marginal deformations of these CFTs, which are JG bar deformations. And from the point of view of gravity, they don't correspond to turning on any gravity fields, but rather they correspond to changing the boundary conditions for these U1 Chern-Simons fields that live on AdS3. In particular, in this case of the free orbifold, as I said, we have the 16 moduli of this T4 and the symmetric orbifold, so those are the usual massless fields that we see in string theory, but we also have 16, in this case, JJ bar deformations that change the volume and the shape of this extra T4, and in addition we have extra JJ bar deformations that mix these two factors together, and there are also JJ bar deformations that only act on the center of mass here of the T4 without acting on the rest of it. So altogether we have this very large 84-dimensional moduli space. And it turns out, I mean, this is a somewhat surprising fact, but by JJ bar deformations, you can start from a current algebra of U1 cross U1 at level Q1 and U1 cross U1 at level Q5. But if you turn on JJ bar deformations that mix them together, then one can continuously transform this at a specific value of the JJ bar deformations to U1 currents that sit at some other values of Q1 and Q5, as long as the product of these values is the same. And in particular, any of these current algebras can be deformed by JJ bar deformations to a place where we have U1 currents of level Q1 times Q5 and an additional set of U1 currents at level 1. So in this way, the deformation is consistent with what I said before. And in particular, what we see is that in string theory, when we move, say, from one of these spaces to the other space, namely, in this case, in the string background, we're turning on the Ramon-Ron coupling. So that turns off on both one of these single trace deformations, but it also turns on some very specific JJ bar deformations that mix the U1 currents in such a way that at this point we get exactly these other combinations of U1 currents that have the appropriate levels to be dual to this CFT. So that's an interesting property of this background, which again just follows from the string dualities.
And the intermediate points, what sort of symmetry do they have?
Intermediate points, the U1s are just mixed together. I mean, so they're always U1 symmetries, but they have off-diagonal terms between them, and so they don't decompose into a direct product like this. It's only at these very special points that the current algebra really decomposes into a direct product like this.
Should be able to describe the symmetries as some holomorphic currents, right? And then I should be able to talk about their levels.
Right, exactly.
So then if the levels change discretely from one corner of the parameter space to the other, in between what is happening? Or are they not there?
Well, the currents are always there, but which currents are left-handed and which currents are right-handed, I think that changes through these deformations.
I mean, we can pick whatever is the right basis, but what would be the, I mean, how would these levels then change in some discrete way?
So in general, so again, suppose you just have some U1 current at some level K1, and you have some leftover current of level K2, and so you start with these current algebras, but then when you add the JJ bar deformation, then I mean it's true that I think that the combinations of currents that are holomorphic and anti-holomorphic become mixtures of the original combinations, and I think these at intermediate points. Again, there are always some combinations. I mean, there are some combinations that have quantized charges, but there are other combinations that will be holomorphic and anti-holomorphic, and they don't decompose in a nice way. It's only at these special points that the left-handed currents and the right-handed currents separately have quantized charges, so that you can discuss the level. I mean, for a U1 level, I mean, if the charges are not quantized, I don't know how to discuss the level, but when the charges are quantized, then it makes sense to ask what the level is. And so there are these special points where the leftovers and rightmovers separately have quantized charges, and then they decouple in this way. So at intermediate points, there are still these U1 symmetries, but the left-handed currents and right-handed currents separately are not quantized, so that I'm not sure how to ask about their levels.
Sorry, Ofer, you said that in string theory, when you do this, it chooses some special values for this JJ bar. But doesn't that depend on the boundary conditions you impose on your string theory?
Well, so those are the natural conditions that you get just from doing string theory on this background. I mean, so the claim is that if we go from if we choose the specific boundary conditions that we get in the SNS string theory with these parameters, then we have these very specific boundary conditions that give us this current algebra. And then when we move away, then also moving away gives us, I mean, it changes the boundary conditions in a specific way. I mean, turning on their one-to-one scalar also changes the boundary conditions for these currents in a specific way. And so the claim is that whenever we have a corner that's described by string perturbation theory, then that string perturbation theory implies some specific boundary condition. Of course, I can always turn on the double trace operator that moves me away from that, but the string perturbation theory itself describes that specific value of these JJ bar deformations. And again, the surprising thing is that that value is not the same in these different corners. So even though each of these corners corresponds to a well-defined perturbative string theory by itself, they don't have the same value of the JJ bar deformations, but different values. So that's just a fact that follows from all these dualities.
And how does supersymmetry work on this?
All these deformations preserve the full 4-4 supersymmetry, I mean.
Including the JJ bar deformations.
Yeah. So I'm not discussing here any deformations that break that. All of these deformations preserve the full 4-4 superconformal symmetry.
Thanks.
So that's the end of the review part of the talk. So any questions about any aspect of these theories before I describe the confusions that we had and how they're resolved? Okay, so I guess, some confusions I already explained before during the review, but let me highlight now. We have 3 additional confusions that are not yet obvious how to resolve. So the first question, if we look at the parameters, so let's consider, say, this special case of Q5 equals to 1. So in this case, we have this free orbifold, and as we said, it's dual to this superstring theory in the hybrid formalism, and the 1/n expansion of this free orbifold maps to the string perturbation theory. And in this case, as we said, the 6-dimensional string coupling is given by general Q5 over Q1, which in this case is 1/n, so it exactly matches to the perturbation expansion, the 1/n perturbation expansion of this symmetric orbifold. But here I looked at the 6-dimensional string coupling. Of course, in this superstring theory, there is also a 10-dimensional string coupling, and that's related to it by a factor of the volume. So I mean, that we suppress the string scale, so it's given by the volume divided by n. And in principle, I could take any value for the volume, and I could even take very large volume, even large compared to n. And at these very large volumes, of course, it is natural to use the 10-dimensional string coupling and not the 6-dimensional string coupling. So we see here that when v becomes of order n or larger, so if v is larger or of order n, then string perturbation theory is actually not weakly coupled, at least in the sense of the 10-dimensional string coupling, even though we still have this symmetric orbifold. I mean, so the symmetric orbifold is dual to the string theory for any value of the volume of the T4, even when I take the volume to be very large. So the question is, how is that consistent with the claim that the symmetric orbifold has this perturbative expansion in 1 over n, but from the string side, it looks like this perturbative expansion breaks down when we have this large volume compared to n.
Sorry, n is defined by this equation by Q5 by Q1. 1 over n is Q5 by Q1 is how we're defining n?
Yes, n is Q1, Q5.
Yeah. Right.
Yes. So there's the special case. This is 1 over n.
Sorry.
So I remind you of briefly of the details of how the symmetric orbifolds reproduce string perturbation theory. So again, this goes back to the 90s. So whenever we have a symmetric orbifold, then we look at specific twist operators in the symmetric orbifold. The twist by a permutation that has a single cycle, so say a single cycle of length w, and then all the others objects map to themselves. So we can have a twist operator involving this permutation in Sn that has a single cycle, and these twist operators are the things that map to the single string operators, or to single string states. And then whenever we have a correlation function, say of some of these twist operators in a symmetric product theory, then we have one of these twist-like permutations at every one of these points. And then we can put together these permutations in different ways between the different branch points corresponding to these twist operators. And putting them together gives us Riemann surfaces. If we look at the covering space, where we have these n copies of our original CFTs, in the covering space, we get Riemann surfaces of different genus, and it turns out that the combinatorics works such that the 1 over n expansion in the symmetric orbifold precisely matches with the genus expansion that we get from the CFT on these higher genus manifolds, so that we can basically identify the covering space of this symmetric orbifold with the worldsheet of the dual string. So in particular, when we have, so the 1 over n expansion, if we have some factor of 1 over n, say, to the power t, then that comes from a correlation function in the original theory. So the contribution of 1 over n to the g to the symmetric orbifold, say, of some m to the n minus n, corresponds to a correlation function in the theory that's described just by the sigma model in M on a genus G Riemann surface. And that's how we get this universal 1 over n expansion for every symmetric orbifold, just by putting together these permutations in different ways. Now, in our case, we have this special case of T4 to the n minus n. So we get here a correlation function in this T4 CFT. And the question is, how does this behave like when the volume of this T4 becomes large? And it turns out that if we have a T4 CFT living corresponding to a very large T4, living on a genus G Riemann surface, then already its partition function comes with an extra factor of the volume to the power G. For instance, if you just consider a single periodic scalar, then its torus partition function for large radius scales like the radius. And similarly, I mean, for any Narayan theory, I mean, its torus partition function scales like the volume. And one can show that similarly, the higher genus partition function of these Narayan theories scale like the volume to the power G. And for that reason, also from the CFT side, we can show that this 1 over n expansion, when the volume of the torus is large, is actually an expansion in volume over n, just like we see in the type 2 string theory. So this way we see that both from the orbifold point of view, And from the string theory point of view, for large volume, the perturbation expansion breaks down, in one case because of the ten-dimensional string coupling, and in this case just because of the zero modes of the field on this very large torus that give us these extra factors of v to the g. So that's how the perturbation expansion is consistent between this free orbifold and the type 2 string theory. However, there's still another confusion here, which is that if this string coupling in the type 2 string theory becomes very large, one might think that we can just do an S-duality transformation and find an S-dual description whose string coupling will be n over v. So that it looks like if v is much bigger than n, it looks like we should have this S-dual description with our own Orr fluxes that should become weakly coupled. But on the field theory side, even though the volume is much bigger than n, we still just have this free orbifold. And I mean, one could ask if maybe the free orbifold for very large volume has this alternative expansion in parts of n over v, but it's easy to compute things exactly in the free orbifold, I mean, even at large volume, and one can show that it does not have any perturbative expansion of this type. So how is this consistent with the claim that in the string theory description we do have this weakly coupled Ramon-Rowan string in this case, with a string coupling, with a ten-dimensional string coupling that goes like n over v. So the point is that we have to be careful in the Ramon-Rowan background with what happens when we take the string coupling to be very small. First of all, if we just naively use the mapping of parameters that we had before, then if the ten-dimensional string coupling becomes small, then also the AdS radius becomes very small. So obviously, we can also trust the usual sigma models. And the claim is that when the Ramon-Rowan coupling becomes small, if Q5 is not large, but the Ramon-Rowan coupling becomes small, then even though it looks like string perturbation theory becomes weakly coupled, in fact, it is not weakly coupled. So the claim is that it's actually not weakly coupled. And this is in fact similar to what happens in another famous example, namely in type 2b on AdS5 cross S5. So also in type 2b on AdS5 cross S5, the string coupling maps on the gauge theory side to the Yang-Mills coupling, and formally we can just take it to 0 and find a zero coupling string theory that maps to the free gauge theory. But we know that the free gauge theory, even though it's free, it still has a non-trivial expansion in 1 over n, and if n is not very large, say if n is equal to 2 or 3, then that expansion is still not weakly coupled, even though naively we took the string coupling in the bulk all the way to 0. So the claim is that exactly the same thing happens also here, namely if in the bulk we take the Ramon-Rowan string coupling to 0, but Q5 is not very large, say Q5 is equal to 1 or 2, then again the claim is that the string perturbation theory does not become free or weakly coupled, but it remains strongly coupled, consistent with what we have here in the dual CFT. So in this way, we can at least avoid having a paradox. I mean, the claim is that even though naively we thought the string coupling, the Ramon-Rowan perturbation theory becomes weakly coupled, in fact it is not, so that everything is consistent. So any questions about this? Okay, so no questions. Let me discuss the second confusion. So the second confusion is again related to the NS string perturbation theory. I mean, since we understand it very well, we can ask detailed questions about it. And when we ask these detailed questions, we encounter some confusions. So the first confusion is already related to the parameters. So as I said, in the CFT side, we had these two discrete parameters, Q1 and Q5, which were evident in our CFT description. However, if I look at the string worldsheet in the SNS background, then in the worldsheet we have this parameter at Q5, but we don't have any parameter corresponding to Q1 on the worldsheet. As I said, we just have some collection of WZW models at level at Q5. And we have a delta field which is massive, and as I said, it should be fixed to Q5 over Q1, but on the worldsheet we don't see that. In fact, on the worldsheet it looks like we do have an arbitrary string coupling that we can turn on, because nobody stops us on the worldsheet from just turning on some coupling to the worldsheet curvature. And nobody stops us from choosing any parameter that we want for this. So it looks like even though in the CFT we have these two discrete parameters, on the worldsheet naively we have one discrete parameter, but we have also a continuous parameter corresponding to the string coupling, which we can choose to be anything we want. I mean, independently of the fact that when we took the new horizon limit, it looked like the dilaton was fixed to something, but nobody tells us this on the worldsheet, and we can just choose it to be anything we want. So first confusion is that it looks like we have this mismatch of parameters between the CFT and the worldsheet, where we don't see this parameter. And so one could say that, okay, maybe the resolution is that there's some non-perturbative effect that causes this parameter to somehow be fixed to some quantized value, but I don't know any non-perturbative effect that actually does that, and we'll claim that the resolution is actually different. Another aspect of this question, which we can see for the case of Q5 equals to 1, is that we can ask some more details about how the string perturbation expansion works in this case. So for instance, if we look at two string, so for instance, if we consider in this case, what is the CFT operator that's dual to a two-string state, then that's dual to a permutation that has two cycles, say one cycle of length W1, another cycle of length W2, and then all the other cycles of length 1. So this would be so the claim, the matching of string theory to symmetric orbifolds tell us that permutations with two cycles are what corresponds to two string states. But if I then compute the disconnected part of the two-point function of these twist operators, then naively I would expect that this two-point function of two string states, its disconnected part should just be the product of the disconnected product of the single string states corresponding to permutations with a cycle of length W1 and a cycle of length W2. That's what perturbative string theory would tell me. But in fact, it turns out that in this symmetric orbifold, that's not true, because here, even though I can glue this permutation to another permutation of the same length, but the combinatorics associated with gluing that is affected by the fact that here, both of these permutations sit in the same Sn with a fixed value of n, and we have different combinatorical factors coming from gluing together these two permutations inside Sn, as opposed to just gluing together each permutation separately. So the claim is that these things agree at leading order in 1 over n, but the subleading orders in 1 over n do not agree if we try to actually compare in detail the properties of the string perturbation theory between the symmetric orbifold and this string theory. So how are these issues resolved? So the claim is that both of these issues are resolved if we conjecture that string perturbation theory does not correspond to the CFT with a fixed value of Q1, but instead it corresponds to a grand-canonical ensemble of CFTs, which is not a standard thing that we look at. But if we denote by Zn of j, say, the partition function of this T4n minus n with some sources j, then we can consider as the grand-canonical ensemble the linear combination of all these CFTs from 1 to infinity with some weight p to the n. And so we can define a grand-canonical ensemble of CFTs just to be this generating function where we sum all these CFTs with different values of n weighted by p to the n. And the claim is that what string perturbation theory actually computes is the correlation functions coming from this grand-canonical ensemble rather than from the ensemble with a fixed value of n, where p is related to the string coupling by 1 over g string squared. So for small g string, we have a very large value of p, and this ensemble is dominated by large values of n, which are of order 1 over g string squared. But in principle, we have here a combination of all of these theories, and we can check that indeed if we try in these worldsheet CFTs to compute what is the central charge of the dual CFT, then indeed we find on the worldsheet. So if you try to compute on the worldsheet what's the central charge of the dual CFT, we find that it's not equal to 6 times n, but rather it's given by 6 times an expectation value of some operator on the worldsheet, whose expectation value is indeed equal to n, but it also has some variance, so that it's not given just by a fixed value in all the correlation functions. And the properties of this grand-canonical ensemble are such that in this grand-canonical ensemble, well, first of all, obviously we do have a continuous parameter, which we can map with this continuous parameter that we see on the string worldsheet. And also in the grand-canonical ensemble, somewhat miraculously, all these problems with the disconnected states exactly disappear, and one can show that when we take these expectation values in this grand-canonical ensemble, all the disconnected correlators do indeed decompose as precisely as expected, with no higher order corrections. So the claim is that the string perturbation expansion precisely reproduces the expansion of this grand canonical ensemble rather than the 1 over n expansion of any fixed of any CFT with a fixed value of n. So questions?
Yeah. Is the fact that is this idea that you're getting the grand canonical ensemble basically a reflection of the fact that the one branes can go to infinity, can go and come from infinity, these long strings?
Yeah, I think it's closely related to that. Yes, I mean, it's partly related to that. I think it's not only related to that in the sense that this happens also for Q5 equals to 1, where we don't really have these long strings. I mean, it's not necessary to have these long strings for this property, but certainly whenever you have these long strings that you may think would take away part of the Q1 flux, then it's maybe natural for different values of Q1 to mix, and indeed they do mix in this way. So maybe let me mention what this means from the supergravity point of view. From the supergravity point of view, as I said, I mean, this n was just some flux living on AdS3. And of course, from supergravity, if I want, I can just work in the background with a fixed flux. I mean, so there's nothing wrong with working with a fixed value of n. And in gravity, that's fine. And even in string theory, I mean, say the string theory in the Ramon background does compute the ensemble with a fixed value of n. I mean, there's nothing wrong with it. But also in gravity, if we want, we can, instead of working with a fixed flux, work with a fixed potential for that flux on the boundary, which corresponds precisely to going to this grand canonical ensemble. Again, it may not be a natural thing to do in gravity, but it's something that I can do. And the claim is that string perturbation theory in the NS background happens to compute precisely this grand canonical ensemble where the flux is not fixed, but it fluctuates, and indeed that naturally meshes with the fact that the long strings can go all the way to the boundary so that the flux is not completely fixed in stone, but it does fluctuate. And that's what we have also in this grand canonical ensemble. So any questions about this?
No question. It sounds a little bit like you're taking a field theory with the sum over parameters. Let's say the Q1 is like some microscopic parameter in your field theory. And now you're defining your field theory as a sum of field theories with different parameters.
Yes.
And that people used to say that kind of thing leads to problems with cluster decomposition or something like that. Now,
yes.
I was wondering what the solution was here.
Yeah, so indeed it does lead to problems with cluster decomposition. So you can show that indeed, because we are in this grand canonical ensemble, then correlation functions do not always obey cluster decomposition. So that's just a fact that again you can show it if you compute in detail the correlation functions to high orders in in the string coupling and so on. You can show that indeed they do not obey cluster decomposition precisely because of the fact that this operator I that in some sense corresponds to Q1. I mean, it does fluctuate on the worldsheet, and its fluctuations lead to contributions to correlation functions that do not obey cluster decomposition. So indeed, it's a strange fact, but it follows. There are many consistency checks on it, so it just happens to be true. Again, of course, it's not. This doesn't happen in almost any other example of the AdS CFT correspondence, and I'm certainly not claiming that it's general in any sense, but these very special SNS backgrounds happen to have this property that they correspond to this ensemble, and therefore they also do not obey cluster decomposition in space-time.
Sorry, one more question. Is there anything we can do on the string theory side to make the string theory the dual of just something with one Q?
I don't know any way to do it again. The Ramon background, that's what it does do, but in the SNS background, it doesn't seem natural to do that. And for instance, you might have hoped that, say, the string theory would be compute for you for some generating function, say, even of the correlation functions for a fixed n. But that's not true. So what the string theory computes for you, for instance, is some derivatives of this partition function with respect to j. Normalized by this as a p of 0. And that's definitely not the same as taking even a generating function of the correlation functions of these fixed n theories, because they're normalized in a different way. So going from the correlation functions of the string theory to correlation functions with a fixed value of n is very complicated. You sort of first have to do a Fourier Legendre transform just of the vacuum amplitude in some sense to get the relation between Zp0 and Zn0, and then you have to do it for the correlation functions. So it looks like it's a very complicated procedure to go from this perturbative string theory to the correlation functions with fixed n. And I don't have any shortcut to that. It just looks like that's not what string theory wants to do for some reason.
Okay, and so the factorization puzzle would not be a puzzle, but a feature of these theories. Is this right?
Well, it turns out, okay, so now you're asking about factorization. If I put the theory on disconnected manifolds, I mean, so there it turns out that actually the grand-canonical ensemble does still factorize. I mean, so this is not like a generic ensemble. I mean, it has some special properties, and the grand-canonical ensemble does actually still factorize when you put it on disconnected backgrounds. So it's not related to that factorization puzzle. That just turns out to be a property of this grand-canonical ensemble on disconnected backgrounds. But I mean, there are various other factorization properties, as we said. I mean, with cluster decomposition and so on. I mean, certainly it does show up in some places, but not in the usual factorization problem. Okay, any more questions about this issue? Okay, so can I have 5 more minutes for the final issue? Okay, so the final issue I want to discuss is the fact that the CFT in this case seems to have this decoupled factor, which is very strange. And so for the case of Q5 equals to 1, as I said, we have this decoupled T4 factor, which looks very strange. I mean, usually we say that in quantum gravity we cannot have any decoupled sectors because everything couples to gravity, and also in string theory, I mean, usually we do not allow us to have any decoupled sectors because the strings couple everything to everything else. But here it looks like the CFT does have this decoupled factor. And I mean, in fact, in some ways it's even 2 decoupled factors because we have this current algebra of U1 plus U1 also. So we have this U1 Q1 to the level 8 and U1, well, and then U1 level 1 to the far 8. And if I look at, so if I look at this coset, then the CFT is really, in this case, we can write it as a product of this coset times, for the semi-direct product, times these 2 current algebras, U1 Q1 to the 8 and U1 level 1 to the 8, where this factor is completely decoupled, while this factor is decoupled, but it's still a semi-direct product because some of the states here are charged also under these U1s. But really, we have these 2 factors that are both, in some sense, completely decoupled. In particular, if we look at correlation functions of the energy momentum tensor here, say of this coset, then they don't feel this other sector at all. So how is this possible to have these decoupled sectors? So the short answer is basically that even though we say that everything couples to gravity so that we cannot have decoupled sectors, these U1 factors, as I mentioned, they're dual in spacetime to U1 Chern-Sammis theories on AdS3. And of course, Chern-Sammis theories famously are topological, so that they actually don't couple to the metric or to gravity. So thanks to the fact that we have here these topological theories living on AdS3, then they are allowed to really be decoupled from gravity, and they are precisely the duals of these extra decoupled sectors that we have here. So in this way, everything does fit together consistently, and we can have these decoupled sectors in a fully consistent theory of quantum gravity.
But the boundary of AdS3? These U1s
yeah, in principle, this could even work on, I guess it could also work on R3. I mean, well, on AdS3 really, I mean, on AdS3, I mean, on R3, the spectrum would sort of be, yeah, and also on R3, I guess if we would have a gap and then we just have these pure Chern-Simons modes, then they would also be decoupled from gravity. But yeah, in this case, on AdS3 in particular, these Chern-Simons theories are dual just to chiral currents, and again, these chiral currents are coupled only to this topological theory on AdS3, and they really know nothing about gravity.
So these modes already somehow live on the boundary, even in the bulk description. Is this right? So,
sorry, can you repeat the question?
even in the bulk description, these modes effectively live on the boundary. So we just see the same modes on both sides.
Yes, that's right. I mean, yeah, you could say that. Yeah, this Chern-Simons theory is topological, but it does have these non-trivial boundary modes, which are exactly these U1 currents and the compact scalars associated with them. But again, they are still completely decoupled. So yes, and in fact, one can show that if one has a U1 cross U1 to the 4th Chern-Sammis theory on AdS4, then that theory by itself is just a dual to a T4 conformal field theory. I mean, so this in general, if we would have some Chern-Sammis theory in the bulk, then its dual CFT would not by itself be modular invariant. But in this case, this vector really is completely decoupled, so it would better also be modular invariant by itself. And it turns out that so these U1 currents are precisely dual just to a T4 CFT on their own, which exactly correspond to this extra decoupled sector. And the rest of string theory describes everything else in this CFT. So everything really does work consistently. I mean, a somewhat surprising fact that follows from this is that string perturbation theory in this case really does not see this extra factor at all. So this factor is completely invisible in string perturbation theory. So not only are there no perturbative string states that correspond to this factor, but really all the correlation functions of the string states with this factor just vanish. So even though we do see this factor in supergravity, and in supergravity we do see these extra U1 gauge fields, in string perturbation theory we do see these other U1 gauge fields at level Q1, but we don't see these U1 gauge fields coming from the Ramon sector. They are really completely decoupled and they just don't show up in string perturbation theory. But again, they are still part of the full CFT and they do couple together. And when we turn on the Ramon fields, again, corresponding to these JG bar couplings, then everything does couple together. But again, all those things are not visible in string perturbation theory. So not only do we have a decoupled sector, but it's also not visible in this case in string perturbation theory, but still the theory manages to handle all of this in a self-consistent way. And again, this property, like the previous one, I mean, it's a very special property. I doubt if it happens in any other cases of AdS CFT, but still it's interesting that in this case, we can study the background in enough detail to see that these properties are really possible and consistent. So yeah, any questions about this?
Okay, sorry, just Chern-Simons theories in the bulk, they come in K and minus K pairs so as to make up a non-chiral spectrum on the boundary?
Yes, so yeah, I guess it should be 1 and minus 1, yeah, that's right. I mean, well, I mean, it's really, I mean, each of those, I mean, so this one corresponds to, say, 4 copies of Q1 sort of AI which DBI in the bulk, where I goes from 1 to 4, so that's what I really mean by this C1 to the 8th, and yes, and then we have a choice of boundary conditions that tell us which combination of those coupled to holomorphic currents, which one's coupled to holomorphic, giant holomorphic currents, and those correspond to the moduli of these compact scalars that are the physical degrees of freedom of these Chern-Simons theories. Indeed.
The boundary protons correspond to the current operator and its descendants and stuff like that, right?
Yes.
What are the modes?
Both the current operators and also all the charge states. I mean, also all this. I mean, in the CFT, the sector has, it has the current operators and also has all the charge states carrying any momentum and winding of this T4. So all of them are just gauge modes of this Chern-Simons theory. They're non-trivial at the boundary.
Yeah, but what are the actual states that are charged under these under the Chern-Simons fields?
So I mean, so in this case where it's completely decoupled, then really the only charge states are just these boundary modes of the Chern-Simons fields. Now that's of course confusing because if you remember, these U1 currents originally came from the Ramon currents. I mean, in string theory, so one might have thought that one would have D-branes that should be charged under them. I mean, but the claim is that even though that's what you would naively expect, in fact, the D-branes are completely decoupled from this U1 Chern-Simons theory, and it's really just the boundary states of this Chern-Simons theory that couples to them. I mean, that's for Q5 equals to 1. For Q5 bigger than 1, I mean, then you do have, I mean, in general, for any value of Q5, then states that have a charge which is a multiple of Q5 can be viewed as boundary modes of the Chern-Simons fields. I mean, so those are sort of fewer gauge modes, but modes whose charge is not an integer multiple of Q5, those are non-trivial states, and those do correspond, say, in this case, to D-branes, or in this case, to winding strings and other states. I mean, so in general, there are various states that do couple to these Chern-Simons fields. But for the special case of Q5 equals to 1, then it's really completely decoupled from everything, and it's just a separate sector of the theory.
So wouldn't these be massive states though?
Again, they just live on the boundary. I'm not sure what you mean by massless.
Okay, thanks.
I mean, the Chern-Simons theory, you can build it as configurations that would be both the currents of this theory and all of the different charge states with any charge. You can construct those. I mean, again, you can compute the partition function of this U1 cross U1 Chern-Simons theory on AdS3. I mean, precisely reproduces the full Narayan partition function of this T4 CFT. So,
these D-branes or whatever that make up the charge states, why can't they move into the bulk?
Well, essentially just because they're pure gauge modes. I mean, of course, it's they only talk to the topological Chern-Simons theory. I mean, they don't talk to anything else. I mean, so you can put them anywhere you want, but I mean, it's most natural to put them at the boundary. Well, states, again, states with charge is not an integer multiple of Q5, those are physical states. I mean, and they can live in the bulk in general, and they, in some cases, they're perturbative string states or D-branes and so on. I mean, so those definitely live in the bulk.
I
Pure
understand.
gauge modes, I mean, it's most natural to think of them as living on the boundary.
No, I understand that the modes of the Chern-Simons gauge theory in the bulk, you can think of them living on the boundary. But what about the stuff that is charged under these guys? Are those also in some sense pure gauge?
Which,
Whatever that is charged under these Chern-Simons gauge fields, why can't they move into the bulk?
so yeah, it depends on the case. I mean, so say we talk about Q5 bigger than 1, then the states, again, the charge states whose charges are integer multiples of Q5, they are pure gauge modes, and they're also BPS states in this case. I mean, and they are not described by any string states or D-branes, they're just pure gauge modes. But other states that carry different charges that are not integer multiples of Q5, those do correspond to physical strings and D-branes that move in the bulk, I mean, and that couple both to the other string modes and to these Chern-Simons fields.
Thank you.
Okay, so to summarize, so I described various features of this type 2 string theory on AdS3 S3 that follow from the fact that we can understand string perturbation theory, in this case, in great detail. And we saw that even though this theory has various strange features, it does manage to handle them all in a self-consistent way. And there are various open questions. One open question is which precisely grand-canonical ensemble do we have for the case of Q5 bigger than 1? So for the case, I described the grand-canonical ensemble only for Q5 equal to 1, where I said that we just weigh all the different states with any value of Q1 with p to the power Q1. But when Q5 is bigger than 1, it's not so obvious which values of Q1 do we need to sum over in the grand-canonical ensemble. Do we need to sum over only those values that are relatively prime to Q5 so that they fit into this web of dualities that I described, or do we need to sum over all values? I mean, those questions are still open, and in principle, by studying in more detail the string perturbation theory, we should be able to answer these questions, but I don't know the answers so far. Then there are many generalizations of this discussion. We can look at type 2B string theory on AdS3 S3 K3. I mean, that's really a relatively straightforward generalization. In this case, the CFT has a point where it's just a symmetric orbifold of K3 to the power n plus 1. And again, string dualities relate that to various other values of the fluxes, so this generalization is straightforward. But other generalizations are less straightforward. There's the case of type 2B on AdS3 S3 S1 that has the large n equals 4 algebra. So in this case, it is still true. Here we have sort of two different values of Q5 and Q5 tilde. And if either of them is equal to 1, then we do still have a free orbifold description. But in this case, there are no string dualities that relate that to other values of Q5. So in this case, we don't really know much about the CFT when both Q5 and Q5 tilde are bigger than 1. And that's still an open question. And yet other AdS3 backgrounds, for instance, if we look at type 2A on AdS3 S3 K3, which is not the same as type 2B on the same background, or if we look at the heterotic string, either supersymmetric or not supersymmetric, again, on various AdS3 S3 M. So in those cases, even the Q5 equals to 1 case turns out not to be a free theory. So in those cases, we know much less about them, and also we don't have these dualities that map Q5 equals to 1 to other cases. So in those cases, there are still many open questions, again, even though the world tree theory in principle is understood for these string theories, but still not much is known about the dual CFTs. Of course, it would be nice if we could understand the dual CFTs, not just in these limits where they're described by the weakly coupled string theory, but also away from those limits for general values of the parameters. But there, so far, it looks like the theory is strongly coupled from all descriptions. I mean, so it would be nice if maybe integrability could be used. Of course, integrability tends to be very powerful in two-dimensional conformal field theories, and one can hope that using integrability, maybe we can learn also about more generic points in this conformal moduli space, maybe about generic values of all these different 20 parameters, but so far it is not so clear. And the final question is, does this teach us any lessons for higher dimensions? In particular, here we have been able to understand in great detail how the string theory has one limit where it's a free theory and other limits where it's strongly coupled. Are any of these lessons useful also for understanding higher dimensions where we have duals to free gauge theories and also to strongly coupled gauge space theories. Yeah, many features seem to be special to this case, but other features perhaps are more general. So thank you very much.
This grand canonical, if it's correct, that one way of making this grand canonical natural is thinking of the branes that can freely go in and out of infinity, then that sort of seems natural in the point of moduli space where there are long strings. Now, when you deform the theory, you turn on some Ramon fluxes or whatever, you no longer have these very light long strings. Then it seems natural to work in this grand canonical picture.
Yeah, so again, I should stress, I mean, this grand-canonical ensemble, I mean, it's really, I mean, it's a feature only of this in SNS description, and also we have, even in different SNS descriptions, we have different grand-canonical ensembles. I mean, so the same background. So for instance, this background, I mean, so in this corner we have the weakly coupled in SNS string and its grand-canonical ensemble. Let's say when its coupling is large, then that description breaks down. Then we have the Ramon description, and for general values of Q5, the Ramon description is weakly coupled. But there we don't have any grand-canonical ensemble. There we just have a fixed value. And if we go to this other corner, then in this corner we have a weakly coupled theory of Q5 equals 2, and that has a completely different grand-canonical ensemble. So there seems to be, I mean, so in the middle, I mean, it doesn't seem like there's any preferred grand-canonical ensembles. I mean, these grand-canonical ensembles are really just features of these specific corners where we have a perturbative and SNS description, and each corner of this type has its own different grand-canonical ensemble. And in the middle, there's really no obvious ensemble to use. I mean, so we should really just analyze each of these CFTs separately. And of course, you can also see from here that it's hiding this whole, I mean, this picture couldn't make sense because this picture depends very strongly on the value of n. I mean, for instance, for prime values of n, I mean, we don't even have these other loci where the CFT is singular. I mean, then there are no other decompositions. Well, if n does have lots of prime factors, then we would have many of these decompositions. I mean, the picture of the moduli space of CFTs looks very different for different values of n, even though they're close together. And of course, the grand-canonical ensemble really just averages over all of them. I mean, so it looks like this grand-canonical ensemble is really just a special feature of a specific description in a specific corner of this moduli space, which is universal to all these values of n. I mean, but if we want to study the CFT moduli space in more detail, then we do have to stick to specific values of Q1 and Q5 because I mean, there's no natural ensemble to use in general.
So suppose I was doing a small perturbation away from your NSNS point.
Yeah. So if it's just perturbatively work in chi, then yeah, then of course it is still described in the group, and there is still a grand-canonical ensemble. But if I would try to take that all the way to some other locus, then it would break down well before that.
For any small, but any finite chi, no matter how small, this picture probably doesn't work.
Yeah, that's right. I mean, it only works perturbatively. Yeah, but that perturbation expansion certainly doesn't converge, indeed.
Ofer, about the decoupled T4?
Yes.
If it's a product, if it linearly factors as a product, why can we think of the charge states as being associated to like the world sheet states? Wouldn't you be just able to peel them off?
Yeah, so they're right. Yeah, so for Q5 equals 1, when it's really completely decoupled, then the claim is that then it's really none of the world sheet states or d-branes coupled to this extra factor. In this case, it's really completely decoupled. But for Q5 bigger than 1, I mean, then again, in the CFT, then these factors are coupled through these JJ bar deformations, so that, and again, they rearrange themselves into these other currents. And for these other currents, I mean, there are world sheet states in this case and d-branes in this case, they do couple to these Chern-Simons theories.
Yeah, let's say I'm just talking about Q5 equals 1.
Yeah.
So
in that case, all the string states are completely decoupled from this factor. You wouldn't see it at all in string perturbation theory.
So the the charge states is simply some charge states in the dual theory of T4.
Right. So I mean, yeah. So since it's completely decoupled, then you can take any state in the rest of the CFT, and then just here add some state that has some windings and momenta on these four scalars, and just in the full spectrum is just any state here times any momentum and winding here, and the dimensions are just the sum of the dimensions of the different factors. I mean, it really is completely decoupled. And these quantum numbers just come from these pure gauge modes on the boundary, coming from this Chern-Simons theory.
Okay. No more questions. So let's thank Ofer again.
Okay, thank you very much, and I hope to see you all in person sometime soon.